Swayam Prabha. Digital India. Educated India.
We are going to discuss sampling distribution today. The objective is to establish a relationship between the population distribution and the distribution of sample statistics. See, the population is huge and it is not possible to test each and every item of a population because the numbers are so huge that it needs a lot of time and a lot of cost may be involved. So we always take samples, and based on the sample statistics, we want to get some idea about the population statistics. What does statistics mean here? Statistics means the parameters, like mean is a statistics. Similarly, standard deviation is a statistics. So most of the time, we take a sample, and the samples becomes a representative sample of the entire population. While choosing the sample, we have to make sure that there is no bias in choosing the samples. So how to avoid bias and how to select sample, that's a different topic altogether. But assuming that we have a sample which is trying to represent the population, then our purpose is from the sample data, if we calculate sample mean, how good it is an estimate of the population mean. Similarly, it could be standard deviation also. So the basis of sampling theory is normal distributions. Now, mean and standard deviation of a function of a random variable. This is some little theory we need to learn before we really get into the way we try to get an estimate of the population parameters from this sample. Before that, just we are going to discuss a bit about few important things, because we'll be using these theories, you can say, for the estimation purpose. So the first thing is, suppose Z is related to several independent random variables x1, x2, x3 up to xk. That means Z is a function of so many variables, independent variable x1, x2, x3, there are independent variables. There are xk, so many k independent variables are there. Suppose the distribution of the variables is such that x1, x2, x3 up to xk have means mu1, mu2, mu3, mu_k, and variance sigma 1 square, sigma 2 square, sigma 3 square, sigma k square. So each variable x1 has a mean which is mu1 and standard deviation sigma 1 square. So standard deviation sigma 1, variance if we say, it will be sigma 1 square. So suppose this is what is there. Then what this theory says, that mean of the variable z, which is a function of x1, x2, x3 up to xk, will be following the same functions of mu1, mu2, mu3, mu_k. So the functional relationships is exactly same. x1, x2, x3 will be replaced by mu1, mu2, mu3 up to mu k. This is one important, you can say, the relationship between the variable z and the variables x1, x2, x3 up to xk. The other important statistics is the variance. Variance, we all know, this is the square of standard deviations. So there is another theory, that is sigma squared z, the variance of z is related to the variances of the random variables x1, x2, x3 up to xk by this relationship which is shown. That is what? Delta z by delta x1 square sigma 1 square. Delta z by delta x2 square sigma 2 square. Delta z by delta x3 squared sigma 3 squared. Like that it goes up to xk. Now there is a proof behind it, but we are not going to get into the details of this proof. We take as it is. So these two are important relationship that we will be using in our as we go through this particular lesson, and hence we need to know them. Now these are basically partial derivatives, del z by del x1, del z by del x2. These partial derivatives are evaluated at x1 equal to mu1, x2 equal to mu2, xk equal to mu k. These equations are true when the function is linear. So this function relationship, when it is linear, that is, this z is a linear function, then only this will be applicable. Let the function relationship between z and the variable or the variables, let us say, is represented by this equation: z equal to a1 x1, a2 x2, a3 x3 up to ak xk. So these are a simple linear relationship between z and the variables from x1 to xk. So from the previous theory, we can write down what is going to be the mean of z. It will be exactly the same functions. F is going to be the same functions with mu1, mu2, mu3, x1 to be replaced by mu1, x2 replaced by mu2, like that. So we can write, if z is related to x1, x2, x3 up to xk by the relationship shown, the equation 1, then mean of z is going to be a1 mu1, a2 mu2, a3 mu3 up to ak mu k. So this is a very, very simple type of equations. And next is, we need to know what will be the variance. So if we recollect the formula which was given in the previous slide, this is the formula which has been used. So we have to use this to find out what is going to be the sigma squared z. We need to find out the partial derivatives. So the partial derivatives, del z by del x1 here for this is going to be a1. For this one, it is going to be a2, and so on. For the last one, it is going to be ak. So if these derivatives are known, then I can write the variance sigma squared z is going to be a1 squared so it is going to be sigma squared z is going to be a1 square sigma 1 square, a2 square sigma 2 square, because all these partial derivatives have to be squared. So A2 is A3 squared and sigma 3 squares. Last one will be AK squared sigma K squared. That is how the variance of Z is related to the variances of the variables x1, x2, x3 up to xk. So sigma 1 represents the standard deviation of x1, sigma 2 represents the standard deviation of x2, sigma 3 for x3 and sigma k for xk. The probabilities of this distribution has been computed and tabulated. By appropriate transformation, one can find out the probabilities of the original distribution of x or sampling distribution indirectly instead of estimating them directly from the original. Now look at this simple functional relationship we have taken. Let's suppose z is x1 plus x2. It's a very simple relationship. So a1 in this case is actually 1 and a2 is also equal to 1. So what is going to be the mu z? So z is a new variable now, which is the summation of two independent variables x1 and x2. So mu z is going to be simply mu1 and mu2, where mu1 is the mean of x1 and mu2 is the mean of the variable x2. And the variance is going to be, if you look back the previous formula, we should write sigma square z in this case is going to be a1 square sigma 1 square plus a2 square sigma 2 squares. Because a1 and a2 are both are 1 in this case, so sigma square z is going to be sigma 1 square plus sigma 2 square. So the variance of z is equal to the variance of the variable x1 plus the variance of variable x2. So you can say variances have a additive property when there is a linear relationship between the new variable and the variances of the other variable. And from there, if the variance is this, the standard deviation is going to be under root sigma square plus sigma 2 square. So it's a very, very simple type of function. There could be a function where x1, z is x1 minus x2. So in this case, a1 and a2, a1 is 1 but a2 is minus 1. So mean is going to be, mean of z is going to be mu1 minus mu2. It's the same functional relationship. And variance is going to be sigma square z is going to be sigma 1 square plus sigma 2 square. Because a2 is minus 1, so it is minus 1 square, which is going to be plus 1. That's why this will be both of them sigma square and sigma 2 square, so sigma z square. So the variance of z in this case and in the previous case are exactly same. There is no difference. So this is this variance, and if you look at this variance, there is no difference between them. They are exactly same. So whether z is connected to two independent variables x1 and x2, if they're connected by a plus sign in one case, they're connected by a minus sign in the other case. In both the cases, the variance will not change, it will remain same. Only the mean values are different. It is mu1 plus mu2, and in this case, it is mu1 minus mu2. So the variance are same. The standard deviation simply will be under root of that. Now, we'll try to make use of this fact to solve one simple problem. Let us say we take two yarns 20 ticks and 30 ticks are their counts, and they are plied together. The count CV of the two yarns are 2% and 3% respectively. What will be the mean count and count CV of the plied yarn? This is what we try to find out. Now here we are assuming that when they are plied together, there is no contraction or retraction. These things, see, in the actual case, when you take two yarns and ply them together, there's a possibility of contraction and or retraction or extension also, depending upon how much ply twist is given and which direction in relation to the single yarn twist. So we will assume that this particular phenomena of twisting and retwisting has no effect on contractions or retraction or extension phenomena of the two individual yarns, as if two yarns are actually lying parallel to each other when they are plied. So the solution in this case will be, what is the mean value? So mean will be very simple. We know z equal to, in this case, x1 plus x2. So mu z will be mu1 plus mu2. So plied yarn count, if that is z, it will be sum of this plus this, that is 20 plus 30, simply 50 ticks. That is going to be the mean. Now in CVs are given, but not the standard deviations. So CV formula is stated here. So if that is the CV, so from there we can write, therefore the sigma is this. So what is sigma 1 for the 20 ticks yarn? We can calculate that, substitute the values, and we get a figure which is 0.4. Similarly, for the other yarn, sigma 2 is 0.6. So the sigma, that is standard deviation of the plied yarn, will be under root sigma 1 squared plus sigma 2 squared, and therefore it is going to be 0.72. That is going to be the standard deviation of the plied yarn. And if I want to know what is going to be the CV percentage of the plied yarn, CV percentage, then this is the CV formula. CV is sigma by mu into 100. So in this case, sigma of the plied yarn is this one. We put it here. And the mu is what? Where is this mu? Mu is 50 ticks. So the mu value will be 50 ticks of the plied yarn. So if we do this, we get a figure 1.44%. So that is the CV of the count CV of the plied yarn. So individual CV of the single yarns are 2% and 3%, and after plying, the CV of the plied yarn is going to be 1.44. So it is much less than the individual yarns. So in the way we have solved it, we are actually using the theory that you have learned in the previous slides. So the same statistical theory is applied here to find out the count CV of plied yarn. Now we can extend this. No, we can have two yarns of one different count and three yarns of the other count. Maybe we are applying 5 yarns, 2 of 20 ticks and 3 of 30 ticks. Then what is going to be the final standard deviations? In that case, that means if I say 2 20 ticks yarn, that means A1 is going to be 2, and for 30 ticks, if you have 3 yarns, then A2 is going to be 3. That means in that case, if Z is the plied yarn count, then it will be 2x1 and 3x2, where x1 represents one particular count and x2 represents the other count of the yarn. So in that case, this is what is your A1 and this is what is your A2. And what about formula that you have already been told earlier? You use the same formula and just substitute the values of A1, A2. You will get the whatever is asked, that what is the standard deviation of the plied yarn or what is the mean count of the plied yarn. You can simply straight away use that formula and get the result. From there, let us go to the next slide. Now, sometimes it could be a function is a multiplication of two variables. It could be multiplication of n number of variables. So we are not going into that complicated things, but it could be. Theoretically, it is possible. It could be x1, x2, x3, x4 up to xk. So the principle is exactly same. Like let us say we can take an example and so also. Like say count strength product. You are all familiar with CSP. So CSP is suppose is represented by Z, and x1 is representing the count and x2 is representing the strength. Suppose Lee count is represented by x1 and Lee strength is represented by x2. So CSP is a multiplication of count and strength. So Z is x1, x2, and we can see that there is an immediate law applications in the case of CSP. So in such situations, how to find out the mean value of Z and the standard deviation or variance of Z? So if we use the same formula, del Z by del x1 in this case is x2 and del Z by del x2 is equal to x1. Therefore, mean will be the exactly similar function. So mu Z is going to be mu1 into mu2. And the variance is going to be sigma 2 square mu1 square sigma 1 square mu2 square. You have to go back to the previous slides where we have written how the variance is related to the variances of the variables. If you use that, we'll get this one. This formula will easily come. Now, if this is how they are connected, if we dividing by mean square, so mu Z square we divide, this is also by mu Z square, this one also by mu Z square, but mu Z equal to mu1 into mu2, so it is mu1 into mu2 square. Here also it is mu1 into mu2 square, and here it is mu Z square, because mu1 mu2 is mu Z. So we are dividing both left hand side and right hand side by the same value. If I do so, now mu2 and mu2 square, they are cancelled here, and mu1 square and mu1 square is going to cancel each other. We are left with this sigma 1 squared by mu1 square plus sigma 2 squared by mu2 square. And this is what is known as relative variance. That is, this is the relative variance of Z. This is the relative variance of the variable x1, and this is the relative variance of variable x2. So when the functional relationship between them is such that it is a product, then the relative variance of Z becomes sum of the relative variance of individual variables x1 and x2. So C square Z equal to C1 square plus C2 square. So this particular formula or theory, whatever you say, can be used in many situations in textiles, where we can say that there is a variable which is connected to some other independent variables. As I said, for count and for CSP is connected to count and strength. Similarly, it could be yarn strength is a function of maybe strength of fiber and the count of the yarn itself, or in percentage how many fibers are there in the cross section of the yarn. So these two may be connected together. So wherever the relationship between the variables is described a product, then this theory can be applied. So that could be situation where z could be x1 by x2. There also z1, if I write z equal to x1 by x2, then also we can use same formula. I can write it as if it is x1 and into x2 to the power minus 1. So again, it is a multiplication of two variable x1 and x2, where x2 has a power which is minus 1. Okay, now from there, if we extend the same thing for k number of independent variables, z is equal to x1 into x2 into x3 up to xk, then mean is going to be also similar, mu1 into mu2 into mu3 up to mu k. And the relative variance squared z will be the summation of individual variances, c1 squared plus c2 squared up to c squared k. So these are very important relationships which will be used in future lessons. Now again we are coming back to sampling distributions. Let the population parameter of a variable x be that mean is mu and variance is sigma square. So it is about the entire populations. And now let us say an infinite number of samples, each of size small n, are drawn from these populations. And we find out the mean of each sample of size small n. And we get the mean, which is x1 bar, x2 bar, x3 bar, up to, suppose say, xi bar. So many means we try to find out. These are the values. The distribution of these means, remember, distribution of the mean is called sampling distribution. So sampling distribution is the distribution of sample means. This is very, very important. Idea is that the population is so huge that we will not be able to, as I said earlier, that we will not be able to find out what is the population parameters, which is mu and sigma. But many a times we can draw the samples, and from the sample mean we will be able to estimate about the unknown population parameters, which is mean and standard deviation or variance, whatever. Now it will be interesting for us to, if we want to estimate that, we need to know what is the relationship between sample mean and population mean, and or similarly relationship between sample standard deviations and population standard deviation. If we can establish a relationship, then you'll be able to get an idea about the population parameters. So theorem 1 states that the population is normal. So this is the first assumptions. And samples are being drawn from this population, and the population mean is mu and the variance is sigma squared. Let us draw samples of size small n from these populations and find out the mean of the sample of size n. So this x bar is summation of individual readings x1, x2, x3 up to xn divided by n. That is what is x bar for only one sample of size small n. So x bar can be written as, it is 1 upon n. I take this n here, 1 upon n as a common, and then write multiplied by x1, x2, x3 up to xn. So x bar is a linear function of x, and therefore mu of x bar is also will be 1 upon n mu 1 plus 1 upon n mu 2 plus 1 upon n mu 3 plus 1 upon n mu n. Since x's are coming from the same populations, therefore mu 1, mu 2, mu 3 and mu n are all going to be the same. And therefore mu x bar can be written as 1 upon n into mu plus 1 upon n into, that means these mu 1s, mu 2, mu 3, they're all basically same and equal to mu because they're all coming from the same populations. Therefore, we replace them by same mu, mu in all the cases. So it will be basically n numbers of mu are there. So it will be mu n divided by n. So it is mu. So mu x bar is going to be mu. So the mean of sample means is equal to the population means. So that is one of the very great relationship between the population mean and the mean of the sample means. This mu x bar, the x bar is there. This indicates the mu is the mean of the sample means. So we have to draw many samples, and each sample has n number of values are there, and we take the average of that, and that becomes my sample mean. So sample mean 1 could be x1 bar, next one could be x2 bar, next one could be x3 bar, like that it can go up to n. And if we now, instead of focusing on the population, if we say now all these means, sample means, also follows a distribution. So what is going to be that distribution? We are going to, we'll be coming to that. But the mean of this sample means is going to be equal to population mean, that is mu. This is the population mean, and this is your mean of sample means. From there, if we go to the variance, we again use that same formula that we used earlier. Sigma squared x bar. So variance of sample means exactly same way. If we remember, it was a1 square sigma 1 square, a2 square sigma 2 square. Here a1 is 1 upon n, a2 is 1 upon n, a3 is 1 upon n. So exactly same that theory we're using here and trying to find out what is going to be sigma square x. So we do this, but because all the samples that is drawn are coming from the same population, therefore sigma 1, sigma 2, sigma 3 all are basically same and equal to sigma. So here also ultimately what it happens? Like sigma square x is going to be sigma squared by n. So that is the relationship between these two. So sigma x bar will be under root of sigma square n. So it is going to be sigma by root over n. And that is what is called standard error. So standard error is standard deviation of sample means. So this should be clear in the mind. What is standard error? Standard error is standard deviation of sample means. That's why we are writing sigma x bar. And this is sigma. So this is for the population. And this is for the sample. Sample means. That is the relationship between them. The standard error is standard deviation of sample mean. That's what I said. And now we will be going for a solution of another example, so that this becomes very clear in your mind. Suppose if we take samples from an infinite population, it is so huge that it is almost infinite. Suppose there is a university where there are 10,000 students are there, and we are interested to know what is the average weight of the students or average height of the students of 10,000 students or 20,000 students in a university. It is almost impossible to really go and take the weight of 10,000 or 15,000 students or measure their height. Something is impossible because it will take a lot of time. It will take a lot of money is involved, a lot of people have to be involved. So that is something which is impossible. So what maximum we can do? We can take samples. That we decide that we, instead of 15,000, we'll only go for sample of 500 students. And then what we can do? We randomly select 50 students. And then take another 50 students, then take another 50 students. So we go for almost 10 samples of 50 students, where each sample is having 50 students. So sample 1 has 50 students, sample 2 has 50 students. So total we go for total 500 students. Or we can decide some other thing, maybe 25 students in each sample, or 10 students for each sample. This can be decided, and there are different logic, what should be the sample size and all. But anyway, let us say in this case, what happens to the standard error of the mean if sample size is increased from 50 to 200 or decreased from 225 to 25? So there are two questions that need to be answered. We take samples from infinite population. What happens to the standard error of the mean if sample size is increased from 50 to 200 or decreased from 225 to 25? So we show you the solution. First, on the left hand side, the solution for A is coming. The formula for standard error is sigma by root n. We all know that. What is, in the first case, the n value, we write it n1 is 50. In the second case, n2 is 200. Because we are changing the size from 50 to 200. 50 to 200. So standard error when the sample size is 50 is sigma by root over n1. We do that. We write it as 0.1414 sigma. Sigma has not been given. So we write it, keep it as sigma. And SE 200, SE stands for standard error. When the sample size has increased, if we do simple formula, we write sigma by root over n2, sigma by root over 200 you get the figure 0.0707. So you see the standard error with 50 and 200. We take the ratio. So AC 50 is more, so we take AC 50 on the numerator and AC 200 on the denominator. Ratio of ACs is going to be 2. So what is the conclusion? That the AC reduces by 2 times. If we increased the sample size from 50 to 200, so we increased by 4 times. Standard deviation decreases by 2 times. So by increasing the sample size 4 times, standard deviations or standard error reduces by 2 times. So that is how will be the answer. In the other case, we want to decrease from 2 to 5 to 25. So it is how many times? In terms of sample size, it is 9 times decrease from 2 to 5 to 25. And due to that, what is the change that occurs in standard error? So standard error formula is given. So N1 is 2 to 5, N2 is 25 in this case for B. So AC 2 to 5 is going to be sigma by root over N1, sigma by root over 2 to 5. It is going to be 0.066 sigma. And for AC 25, it is going to be sigma by root over N2, that is going to be 0.2 sigma. And we take the ratio of ACs, AC 25, 2 to 5 and AC 25. It will be 25 by 2 to 5. So whichever is larger, we'll keep it at the top or the numerator. So it will be 0.2 sigma by 0.066 sigma. And this gives a figure 3.03. So AC increases by 3 times. So by reducing the sample size from 2 to 5 to 25, the standard error increases by 3 times. That's what will be the answer. So this is how standard error changes as we increase or decrease the sample size. Next theorem is central limit theorem. This is a very, very powerful theorem, and this has a lot of applications. It may so happen that nature of the population distribution is unknown. Most of the time, that is what is going to happen. What is the distribution of students' weight or their height? It is unknown to us. We may assume that it is normal or something else, but that's an assumption. So suppose in many cases we don't know the exact nature of the population distribution, which will remain most of the time unknown to us. But let us say now the population mean is mu and the variance sigma squared, this is known somehow from the past data. Suppose we know this. If one draws samples of large size as n tends to infinity, that we take the samples of 10 and then 20, then 50, then 100, then 200, 500. If we keep increasing the sample size, distribution of the sample mean will be normal. So mean of sample means mu x bar will be sigma xi bar by n, which is going to be mu, and the variance of the sample mean sigma square x is going to be sigma squared by n. Therefore, standard deviation of the sample means sigma x bar is going to be sigma by root n, which is also known, this is also known as standard error, which we have already stated. And the variable z, I think we have discussed it earlier. Z is a standard normal variable, and we can write that xi bar minus mu by sigma by root n will follow standard normal distribution with mean equal to 0 and standard deviation 1. So it becomes a z variable. This z is basically standard normal variable, that is z. So z is x by xi bar minus mu sigma by root n. This will approach standard normal distribution. That is what is the interesting part of this, that even if the population distribution is unknown to us, but if we take samples, find out the mean, and if the sample size is little large and we keep plotting the distribution of the sample means, we'll find it to be almost normal. And if we go to the next slide, that's what it shows. Now, suppose the original population distribution is exponential, shown here. And if we take samples of size 2 and then find out the means, and the means we plot, it looks like this. It still remains exponential in nature. If we take 5 samples and find out the mean and then plot them, the shape changes. And if we go for 30, the shape becomes close to normal. It becomes symmetric and close to normal. That means as we keep increasing the sample size from 2 to 5, 5 to 15, maybe 20, 30, and if we go 30, close to 30, a little more than 30, the distribution of sample means will be very, very close to normal. That is what basically it is saying. For uniform population, this diagram is not correct. If we take n equal to 2, and this is the distribution of the sample means, my sample size is 2. If we go for 5, it will look like this. If we go for 30, the distribution will be symmetric and very close to normal distributions. So irrespective of the original distribution, which is maybe exponential, maybe uniform, maybe some other distribution, the distribution of the sample means will be almost normal if the sample size is large, that is close to 30 or more. That is what it is saying, that sample means follow the normal distributions irrespective of the distribution of the population from which the samples have been drawn. Application of sample, the central limit theorem. Let's say Z be a linear function of k independent random variables. So Z is a1, x1, a2, x2, a3, x3 up to ak, xk. The distribution of Z will tend to be normal almost irrespective of the form of the distribution of x, provided none of the variances sigma 1 square, sigma 2 square, sigma 3 square, sigma squared is large compared to the sum of the rest. So this is also basically an application of the central limit theorem, that if z is a variable is related to the variables x1, x2, x3 up to xk by a relationship shown here, which is a linear function, the distribution of z will be normal irrespective of the form of the distribution of x, provided none of the variances of x1, x2, x3 are large in compared to the sum of the total variances. The greater is k, the closer will be the approximation, that is approach to normality. An example, if we take like this, when we try to measure the yarn count, there are many sources of error in count measurement, like measuring length. Measure the length of the yarn for count determination. There could be some error in the measurement of length. Some yarns are stretchable, so with a little stretch it will extend. There are many sources of error. Measuring weight, while determining the weight on the weighing balance, the balance itself may not be giving you the right weight. Due to some reason, it may give some wrong weight. So that is possible. Sampling error, piece of the yarn segment that has been chosen. That is, the sample that I have chosen, I may be biased in choosing the sample. That suppose that is a cone, and you have been asked to find out the count of the yarn from the cone. If I remove the yarn from the top layers and measure the count, I get some value. But if I don't remove yarn from the middle layer or the end layer, then who knows that the middle layer yarn count may be different than the yarns which are there on the top layers, or at the bottom of the cone, that may be counts may be different. So this is called sampling error, that I am taking samples. While taking samples, I am biased. Whatever may be the reason, but I am biased because I am only taking the yarns from the top layers, or I am only choosing yarns from the good looking cones and discarding the cones which are not so good looking, or there is some defect in that. So there are many ways that we get biased while choosing. So there are many ways sampling error could be there. Then variation in the raw material, that could be also a source of variations. Now if each independent error is relatively small, then each individual observations can be written as that x is an independent observation is true value of count plus the error which is arising due to these reasons. So mu plus e, where error e is made of linear combination of independent error e1, e2, e3 up to ek. So the error for each measurement would be due to k number of errors. So we say E is a linear combination of the errors arising for maybe measuring length, E2 may be due to measuring weight, E3 because of my sampling error, E3 or let's say EK could be because of variation in raw material, and one can add here is you have shown it to be 4, it could be 5, it could be 6, it could be whatever it is. So because it is a linear combinations, linear function, therefore the central limit theorem refers to this, and thus we should expect a normal distribution for the yarn count. So if we take, let us say, measure the yarn count from a cone, you take 100 readings from the top layer to the bottom layer, and if we plot those data, you will find that it is following normal distributions. And that is because of this reason. The errors which are coming into my measurements because of so many reasons which are there, there could be variation in, so let's say, humidity also. No? So the top layers will absorb more moisture, the bottom layers have not absorbed much moisture. So that could also lead to some variation in the wet, and therefore some error inherently there in the measurements. Finally, when we find out the count, there is true value and the error is there. The error is normally distributed, and there are so many individual errors which are coming and getting added together, and the E becomes by the total error in one particular measurement. Therefore, the value in this case, the X is going to follow a normal distribution. That is what the theorem says. Now we go for an example. A part of a garment is made by joining two pieces of fabrics, A and B, end to end. The specified length of completed part is 60 cm with tolerance 2 cm. The length of A pieces are normally distributed with mean 20 cm and standard deviation how much? 0.5 cm. While the B parts again normally distributed with mean 40 and standard deviation 1 cm. This is what is given. What proportion of completed parts will meet the specified tolerance? That is 60 should be total with a tolerance of 2 cm. So we have showing A part normally distributed, B parts are normally distributed, and having their own mean and standard deviations. So mu A is 20 cm given, and sigma A 0.5 cm also given. Mu B is 40, sigma B is 1. So these are already given. Now we need to know how T is going to change. So T is a linear function of A and B. So here there is a variable A, there is a variable B, and T is the summation of two variables, independent variables A and B. So exactly what we have already discussed earlier, Z equal to A1 x1 plus A2 x2. So we need to know what is going to be the mu value of T. So what is mu T? Because it's a linear function, mu T is going to be mu A plus mu B. 20 plus 40, which is 60. So finding out mu T is extremely easy. It is the sum total of the individual mu value of the variables which is there on the right hand side. And sigma squared T. So this variability also we are interested to know. And here it is going to be sigma squared A plus sigma squared B. This also we have learned earlier. And you put the value of what is sigma squared A? 0.5 square, 0.25. 1 squared is 1. So sigma squared T is 1.25. What is sigma T? Is 1.118. That is my standard deviation of this. So now we need to know what is Z value. the tolerance is given 60 plus minus 2. So it could be 58 to 62. So if I say 58 minus 60 divided by the standard deviations 1.118, I get a figure minus 1.78, and Z2 is plus 1.78. So now mu t is normally distributed. So T is normally distributed. This is, you can say, T. And this is my mu T, which is actually 60. So where 58 lying is here and 62 is here. This is the range. We want that when the two pieces are joined, the total length has to lie in between 58 and 62. So what proportion of the product is going to lie between these two limits, 58 and 62? That means we need to know what is the area in between 58 to 62. So we try to find out what is the Z value corresponding to 58 and what is the Z value corresponding to 62. That's what we have found out. Z1 is going to be 1.78 minus side and Z2 is going to be plus 1.78. The proportion of parts that will meet the specification, and this area, for these values of Z, we can check the Z table. So we have to consult the Z table which is given. From that table, we can find out what is the area beyond 1.78 plus 1.78. Here Z2 is plus 1.78. What is the area beyond this? This figure is 0.0375. So this figure also, because in Z scale they are same. In Z scale, here at the center Z is 0. So on this side it is 1.78. On the other side also it is minus 1.78. So this area will be also equal to 0.0375. So both side area will be 0.0375. Therefore, the area in between 58 and 62 indirectly means the area in between minus 1.78 and plus 1.78, that is Z1 and Z2, is going to be 1 minus this, which is equal to 0.925, that is percentage wise it is 92.5%. Then when 92.5% of the joint pieces will meet the specifications. So many a times we join together the fabric pieces to make a garment, or we want to make something else, that we need to join the pieces of fabrics together to make some product. So where there the variability may come into play, and therefore there is every possibility that some of those final products may meet the specification or may not meet the specifications. And this is how we can find out. So we close the session today just now, and next we will discuss the distribution, which is very again popular and very useful for us, that is T distributions. So we'll learn more about T distributions, and then we'll come to chi-square distributions, and then we'll come to F distribution. There are three more distributions which are very relevant and very important for have a proper understanding of the statistics, and you'll find there are many applications of this in quality control or in process control. So we are going to discuss all this in the next class. Thank you.